From now, this time, we will continue to learn about the shield channel effect. Last time, we learned about the basis of shield channel effect. And so, we learned about the punch-through phenomenon. This time, we'll learn about two more shield channel effects, and then we'll know how to solve this shield channel effect. So by the solution, we will learn two things. And last it is we will learn about various field effect transistor except of the MOSFET. So let's start with the VT roll-off. The VT roll-off is from the long channel from here. Let's see this paragraph. If the device has a long channel from here, the VT remains constant from here. But when the channel length getting shorter, there has a situation that the threshold voltage getting down. So it is similar to the roll off from here. So we call this situation the VT roll off. So the reason why the VT roll off has emerged, it can explain it by the charge sharing model. So when the device has enough long channel from like this, the depletion region is like this. But when the device getting shorter, like this, it's getting shorter, there has a problem because there has a vertical depletion region by the MOS structure from here. So depletion region will make like this region, and by the between the substrate and drain source, the horizontal depletion region remains like this. So there has the region that overlap the depletion region. So when the depletion regions are overlapped, the electric field is getting higher. So when we give a little gate bias from this device, it can easily make the channel from here. It means the threshold voltage is getting lower, so the VT, the threshold voltage, getting lower like this. And as you see, when the drain bias is more higher, the VT roll-off phenomenon has getting higher. So you can see that when the drain bias is 0.1, the threshold voltage getting down like 0.2 voltage, but when the drain bias is 2.5, the gate bias is down almost 0.3 volts. So when the drain bias is getting higher, the VT roll-off situation also getting higher. The second through channel effect is velocity saturation. As you already know, this formula J equal Q and mobility and electric field. And we also already know that the velocity V equals mobility by electric field. So we can draw the velocity V and electric field relationship. We can easily think that the relationship is getting a linearity because the slope is mu, it is a mobility. But in real, when the electric field is enough too small, it can remain the linearity. But when the electric field goes through the critical electric field, it starts to saturation mode from here. It is the velocity saturation. From the short channel device, as I explained the charge sharing model, from here, there has a lot of electric field from here by overlap the depletion region. So it can easily go through the critical electric field when the short channel device. So there has a velocity saturation phenomenon from here, and it means the mobility goes down because when the velocity and electric field relationship are linear, have a linearity, the mobility is constant. But when the relationship between V and E has a saturation region, the mobility is degraded. So we can also call this phenomenon as mobility degradation. So this time we learned of 3 short channel effects. The first was punch through. The second was VT roll-off. The last thing is velocity saturation. It equals mobility degradation. So that's are the one we call this situation of the short channel effect. So how to reduce this short channel effect, we can reduce by using the two types of junction engineering. The first is lightly doped drain. It means by the lightly doped from here, we can reduce the electric field. Why we reduce the electric field is the short channel effects are due to electric field. So if we solve the problem, we will reduce the electric field from the channel. So if we doped lightly from here, we learn the depletion reason when we learned about PN junction. From the depletion region, there has a fixed charge from here, and by the fixed charge, it makes a built-in electric field. But when we doped lightly, the fixed charge remains lower, so electric field is also lower. So by using the LDD junction engineering, we can reduce the short channel effect. The second thing is pocket implant. We can see these two new junctions from here. We call this region pocket junction or halo junction. By put this junction like this, we can block the puncture situation, and also we can also block the another short channel effect, because that junction makes lowering the electric field. So by using two junction engineerings, LDD and pocket implant, we can reduce the short channel effect phenomenon. And last chapter is various field effect transistor. There has a lot of field effect transistor from now on, so I will introduce for 4 things about FET. The first is HKMG. It means high K metal gate. It is not much different from the MOSFET, but the different thing is in HKMG, it doesn't use oxide from here. Instead, we use a high K material. By enhancing the device, it is important to make the capacitance more higher. The capacitance is epsilon thickness by area, but in the device we doesn't consider the area from here. So when the capacitance goes higher, we can do 2 things. First thing is the lowering the thickness, and second thing is higher the permittivity. But from this thickness, it has a limitation to lowering the thickness because when the MOS structure, when the oxide thickness is too thin, it can make a tunneling effect from here, so it makes a leakage current. So the other solution is to higher the permittivity. So we use another material that have a high permittivity. So that material, we can call that high K material. So by using this material, we can enhance the capacitance. And if we use a high K material, we also use the metal gate. The reason that use a metal gate is the metal has a equipotential. When we use a polysilicon from the metal, from this surface, there has an interface trap from here. So by this interface trap capacitance, it lowering the subthreshold swing. So if we use the metal gate with high K material, we can enhance the subthreshold swing, and the gate coupling is getting more better. The second another field effect transistor is HEMT. The HEMT means high electron mobility transistor. From now on, we used silicon to make a transistor, and the silicon is group 4 material. But the silicon has a disadvantage. Its mobility is not too much good. So by using the group 3 or 5 material, we can enhance the mobility. So by using group 3 and 5 materials, we can make a transistor. So it is a HEMT. But nowadays, we can't usually use this transistor. The third is JFET. A JFET is similar with the MOSFET, but the different thing is there has a lot of junction. So let's see the JFET construct. From the N-type JFET, there has a drain and source like here. And the different thing is they have another junction from the middle of source and drain and bottom of substrate. We doped a heavily doped p-type, and the another difference from N-type MOSFET is we use the lightly doped end for substrate. So if you make the device like this, the depleter region is made it like this. So this is when the gate bias is 0 and when this JFET is enhancement mode. By the depletion reason, it can't make a channel, so it doesn't work. But when we give a gate bias from here and here, we use this two reason like a gate. And when we give a gate bias from here, the depletion reason is like this. So it can make a channel from between the depletion region. So by using this JFET, we can make a channel by giving the gate bias. And also when we manipulate the depletion region like this, when the gate bias is 0, it is a depletion mode JFET. Last is a MOSFET. MOSFET means metal semiconductor field effect transistor. It means it doesn't have a oxide layer from here. It only have a metal from here. And this is a MOSFET. So this time we reviewed the various short channel effect phenomenon, and we also learned the solution that reducing the short channel effect, and we also know about the various field effect transistors.